Okay, good morning. Let's have a class. This will be our second class, and we will continue to talk about exam 1, slide 1. We'll talk about the histories, and we move on to some of the real material. So I moved these slides up because during the pandemic, everybody is talking about the vaccination, whether we should get a vaccine of COVID-19. So I moved the slides up, give you a little bit of information about the history of the vaccination. Okay, so we talk about the vaccination. So first of all, the vaccination, this is coming from a Latin word, VACCI, originally is VACCA. This means, in Latin word, it means cow. So there is some story behind that. It's related to a very important Great Britain physician, Edward Jenner. And he is a medical doctor working for the Royal Society in London. Lives in the suburb of London. Back in like 1700s. So what happened is, by the time there is a very contagious virus called smallpox. It's a smallpox virus. Smallpox virus, it belonging to a group called variola virus group. Later on, we also call it a smallpox group. So what are the symptoms of the smallpox? It is where we will have vomiting and fever. That's very usual. However, it will be accompanied with very progressive skin rash. So what happened is, if somebody had a smallpox by the time, their whole body, the skin is a red dots, is a red rash. And even they recovered, they still gonna have the same symptom, which is we call it a sequela, have a progressive skin rash, even you recover. Now by the time, there is no way to do. The only way they do is put those people, they're isolated into an island. So somehow like a movie, like a shut island, they put people there. And the whole mask is covered the face. Because part of the reason it looks ugly, because it's a progressive skin rash. So it bothers the Royal Society and the Great Britain a lot. So what are they gonna do? They tried the medicine, it didn't work very well. And we mentioned vaccination somehow is the best way to control virus. So this guy is going to search around to see some way to do. He found it's very funny. And although people are struggling with smallpox, but there is a group of people, ladies working at dairy farms, they'll survive. However, most of them have a very mild symptom, which is called cowpox. The cowpox virus is the same group as variola virus with smallpox, but it's very mild. Do you know the death rate, mortality rate of a smallpox? It is around 30%, which means if 100 people who get smallpox virus, 30 of them will be die. That's a basic statistics. What is the death rate of cowpox? Around like 0.1 to 1%. Well, it's still very high, but by the time it's very low. And he found the ladies working at the dairy farms had cowpox, they're fine, and then he got what kind of thing is called lean from the cowpox virus infected woman, and then he got the extract. The lean extracted from the cowpox and used to inject a boy, give some preventive measurements, which is a vaccination. And then the boy further infected with smallpox virus, and the boy survived. So that's a story. Because we want to memorization, Edward Jenner, later on, we call this whole process is vaccination, and the VACCI, which indicate a cow, because originally it's coming from a cowpox, to concave and proactively prevent smallpox virus. Smallpox virus cause the symptoms has been devastating. So once this cowpox vaccination generated, it saves millions of people, trillions of people's lives. And the last case showed in the world is 1977. Originally, this comes out in 1500 BC somewhere in Egypt. Then back in 700 years, it's in a European country. It's a pandemic, horrific pandemic. Because of the vaccination, the last case showing up is 1977. Then in 1980, forward, there is no any case has been reported. So WHO somehow in 1982 has been declared smallpox virus is eradicated, we say it, which means it's gone. And we concaved and we win the war with smallpox virus. That's the initial story of the vaccination. And we know that there is a different type of the vaccination. So basically the vaccination is give you somehow is a small dose of the toxin and to stimulate an immune reaction in your body, and hopefully it will generate an antibody because there is an antibody-antigen reaction. And the antibody could be stay there a very short time. That's why we need another shot, and we call it a booster. Some of them, we only need one shot in your lifetime because that kind of vaccination is activated you B-cell activation line, which is have an antibody, have a longer time, okay? So remember, if we talk about immunology, we will talk about later on more detail. There is two lines, which is T-cell line and the B-cell line. And the humoral immune is B-cell line. And the cell-mediated immune is T-cell line. And one of them, the B-cell, will generate an antibody that stays a little bit longer, and T-cell line is only some of the natural killer cells combined with macrophage. So that's why we need a booster all the time. Now the technology has been developed, we have some of the new methods. Let's say the coronavirus, the Pfizer and the Moderna, both of them, they get is RNA virus, which is a S protein from a coronavirus. And I will say it's pretty successful. Okay, without that, some of the positive patients will be going to die, but they can survive very well. And developed today, it's become a very mild symptom. However, because vaccination, more or less, there are some toxin in your body, is that right? So not many people will accept that. So we respect those type of the decision. That's why it is people's choice whether you're going to have a vaccination or not. So that's some story and some background about the vaccination. Okay. Next one, discovery of microorganism. This is a very important, the milestone in the microbiology history. We want to talk about a person, Anthony van Leeuwenhoek. Whenever you see the middle name of VAN, like a van, most likely this guy coming from Netherlands or Belgian area. And Anthony van Leeuwenhoek is the first person who create his own mechanic microscope and do the observation of the microorganism and record it. And recorded it. That's very important. When he recorded it, he submitted this to the Royal Society of Great Britain. That's why it's been recognized as the first person who is find a microorganism. So for himself, he's an amateur scientist. Most of the time what he did is selling the clothes in the western of the Europe, so he's a typical businessman. But in the amateur time, he wants to do some of the science studies. So he created this mechanic microscope. You see there is a holder, there is a lens, and you can also do the observation. Now what we really care about is what is the magnification of his study. Later on, people find that the magnification of Leeuwenhoek's microscope is about 30 to 200. That's not too much. We mentioned in the lab the oil immersion with 100x microscope is showing you 1000 magnification. So this is barely 30 to 200, not that too much. And when the paper submitted to the Royal Society of Great Britain, he said what he find is bacteria. And some of them called protists. So you see those lines there, something like this, something like that. Like a protozoa, like a bacteria, but later on people find it is actually a structure of the bacteria that is a bacteria flagellum, which is the structure for bacteria to do the real movement. Okay, so it's kind of interesting. A little bit of gap between by the time what he did is observation and finally is recorded in the history book. But anyhow, that's a breakthrough in the microorganisms because we need to see the morphology of the bacteria and the movement of the bacteria, and that's very important. Then we can go in more deep to see the genetics, biochemistry characteristics, all those things. However, history also have some criticism for him. Yes, he is a businessman. Lots of people want to have the ownership, or we say the copyright of his microscope. He refused to sell it. So the microscope did not become popular by the time in the Western Europe. Therefore, it delayed the development of the microbiology area about like 100 to 150 years. So you can see here, Anthony van Leeuwenhoek, the time is 1600 to 1700-ish. And when we go later, when you see the golden area, Louis Pasteur, 1800, almost to 1900. You go here, Bob Koch, 1900. There is about 150 years gap because of the lack of the popularity and availability of the microscope. Okay, But anyhow, we still think it is a good contribution for the whole world, which is create mechanical microscope and do the first observation and the record of what he finds. So this is Anthony van Leeuwenhoek. Next one, we want to talk a little bit about spontaneous generation. So I'm going to have to remove these. I want to talk about here. It's a very cool studies in the scientific world at the beginning stage of the microorganism and showing some of the wisdom there. So we want to talk about spontaneous generation. First of all, what is spontaneous generation? Spontaneous generation, which means a non-live matter create a life body. So very simple example. A decayed meat generate a larvae and a fly. An air will create a bacteria. Now, lots of people still believe it even today because of the political or religious reason, but in the scientific area, they will have been battling a long time, maybe a couple of 100 years to try to solve the problem, especially in the microbiology level. So first thing we need to introduce you to is that how spontaneous generation repel at an organism level, which is by a very important Italy scientist Francisco Redi. He did a very interesting and a very important research is related to a raw meat, generate a maggot, and finally is a fly. Of course, that raw meat is a decayed meat. So here is the story. We want to really focus on the experimental design. I think it's very interesting. Okay, first step. I had a meat. Let's just say I had a meat. Okay, it's a decayed meat. It's a raw meat. If this raw meat stay in the room temperature, exposed to the air, later on what is going to happen? This raw meat will become spoiled, and the fly gonna come in, some fly gonna come in, they will generate some of the maggots, and the maggots will generate, actually it's a larvae, and then finally become another fly. Okay, then people will say, it's very similar, seems like a raw meat generate a fly, is that right? Because we put a raw meat there, exposed to the air, okay, couple of days, fly comes out. Makes sense, a raw meat generate a fly. So we need a control group. What are we gonna do? I have another raw meat. And this time, instead of it exposed to the air, I'm gonna cover it. I'm gonna completely cover it using a paper. Once you're covering a paper, what happened? Nothing is there. This fly did not generate. Well, so I can argue it's correct. Because if I cover with the paper, no fly comes out. Which means this meat did not generate a fly. So there's no spontaneous generation because otherwise the fly will still come out. But then people are going to be arguing. Maybe it's an air generated fly. You cover with the paper so there's no air, so the fly is not come out. So he had a very magical design right here. It's the same thing I had a raw meat. Now what I'm going to do, instead I put a solid paper, I'm going to add a cheesecloth. Cheesecloth, you know that, some medical cheesecloth. There is a space between that. So what this tells you, the air could come in. However, the fly will not be going inside. So is there air? Yes, there's air. Is there fly generated? No. However, later on, when I remove this cheesecloth, if I remove it, then it will become a naked meat. A naked raw meat. It repeated the same thing right here. So that tells you both a raw meat and an air will not automatically generate a fly. Why the fly will comes out? Because some of other fly lay down some of the spoiled, some of the maggots there. The maggots become a larvae and later on become a new fly. That's what happened. So this is a very magic design of the experiment, and from the organism level, it repels the spontaneous generation. But how about in a microbiology level? This gives people trouble. So by the time people does not have many of the control methods to really killing bacteria, so what they do? They're using a flask, let's say, okay, an easy flask. If in this flask, I'm going to add in some of mutton broth. Okay, then I broil, let's say 100 degrees Celsius for like 15 minutes, let's say. Okay, then I cool down. Later on, what I find, it becomes still cloudy. Which means they still have a bacteria or microorganism could be there. This is what found by John Needleman in 1950s, 1960s. So John Needleman found it like that. Even a mutton broth boiled, it will still have a crowded microorganism could be generated. So he said there is some viral force to trigger the generation of microorganisms from a mutton broth. Now another scientist, which is from Italy, Lazzaro Splazzini, he did the same thing. A flask. Instead of using mutton broth, I use beef broth. I'm going to boil at 100 degrees Celsius, a little bit longer time, 45 minutes. And later on, what you find, what do you find? This is clear. Nothing growing. Very transparent. We will talk about in the lab, if we have a broth, a bacterial broth, let's say a nutrient broth, the very obviously phenomenon you can see a bacteria grow or a microorganism grow is become turbidity, become cloudy. And if no bacteria grow, no microorganism is there, it is very clear. And the transparency, transparent. So he found that a different story. Therefore, he said, spontaneous generation is not working in a microbiology level, which is correct. Now, later on, people know about that. The broil methods does not mean you're going to kill all the bacteria. Is that right? Some of the heat-sensitive resistant bacteria will still survive. some of the endospore bacteria. The bacteria has endospore will still survive. But by the time, they don't know. So there's a big debate by the time. And lots of the labs, they repeated the same thing. They find totally different, opposite results. Until this guy comes out, is Louis Pasteur. Louis Pasteur has a very dramatic and very smart method. What he did is called this swan neck experiment. The swan neck jar or swan neck flask. So what happened is, these are just a traditional flask. So let's say I'm just draw a flask, okay, like this. It's a traditional flask. What he did is, instead of we only had a little bit extra on the top, topping on the top, I'm going to extend this one like that. Like a neck. And this morphology looks like a swan, so we call it a swan neck. It's right here. The key thing is here. So what he did the research. Same thing. I have a broth. Of course, the bacteria are going to be there. Okay, so I'm going to broil. Boiling 100 degrees Celsius, let's say 20 minutes, a little bit longer. Okay, after that, I have two groups. One group, I'm going to break down it. So, the same thing, right here. A swan neck like this. However, I'm going to block it. So I remove this part, then the broth become cloudy. Why? The reason is the bacteria or microorganism from the air comes in and it starts to grow. But at the same time, I have another group. I did not break this swan. So what happened is, this swan neck is still there, and this broth, which is showing you completely clear and transparent, and nothing seems like grow. Why? There is a bacteria there. The bacteria is hiding in the side or the edge of the swan neck, did not get chance to go in through. That's why this broth is completely clean. And because of that swan neck flask, it is repel the spontaneous generation in the microbiology level. Then lots of people continue to do the research, try to verify it. When you have some research published or somehow announced, people have to do a more verification study to verify it is true. So different labs in the world start to verify it. Some successful, some did not successful. Now we need somebody at the end to tell us, yes, it is true. What they do, very late, about 50 years late, John Tidal and Ferdinand Kohn, both are German scientists, did a great contribution for that. They find that why the boring methods will cause a different results. Because they could have heat-resistant bacteria. So today we easily understand that there's a heat-resistant bacteria. Did you ever go Yellowstone National Park in Wyoming? When you go to those hot springs, there's lots of bacteria still there. It is more than 120 degrees Celsius. Why? Heat-resistant bacteria, is that right? For the hot spring. Now those bacteria, we usually call it an environmental microorganism because it's resistant to the heat. Naturally, there are some specific enzymes that could be used. And there is another bacteria which is, we know it's heat resistant, called Geobacillus. This is the one we usually use to do the QC, quality control, and the quality management of the autoclave. We want to see whether the autoclave machine is still working. Because if the autoclave has not been reached 121 degrees Celsius, then the Geobacillus will still survive. Which tells us even you use boring method, this Geobacillus is still there. So that's the first thing. The second thing could be, we just mentioned, is bacteria has endospore. If the endospore bacteria, then they will be survived in the heat treatment. A good example is Bacillus. Another good example is Clostridium. So we will mention in our exam 2 a very detail about the Clostridium, including Clostridium perfringens, Clostridium tetani, Clostridium difficile. All these pathogens are related to Clostridium. We will introduce you. It's a typical endospore bacteria. So start from here, you can see it took a scientific area about 150 to 200 years, finally in a microorganism level, to repel a spontaneous generation. So it's a lots of work there, and a lots of the magic things they do, and a lots of the cool research they've done. Okay? So that's a final blow to theory of spontaneous generation. Next one, we want to talk about this very big person in the scientific area, is Robert Koch. So we want to talk about right here. Bob Koch is a German scientist. He is the first person to talk about the pure culture, and we will practice that in the lab. And he's the first person who generated a theory called Koch postulation. It is well explained the relationship between a microorganism and a specific disease. So we want to talk about this called Koch postulation. So the history is going, and people find the microorganism is going to be generated, not spontaneously. Somehow coming from environment, come from disease, it causes all the problem. But we want to give the treatment for the microorganism. We need to know the relationship between a microorganism and a disease. So Bob Koch, a great German scientist who's mentioned this postulation. It's a theory. So what is the theory? Number one, I said very simple. Healthy people or healthy organism absence of certain microorganism will cause specific disease. So there is a very good example, which is using Mycobacterium tuberculosis. Mycobacteria tuberculosis. Tuberculosis. Or we just simply say it is TB. So what this means is a healthy people should have a TB isolated in his or her lung area or the sputum sample. So that means healthy people, absence of TB. Of course, sick people, present TB. That's the first thing. The second thing is that specific microorganism can be isolated from sick organism and get pure culture. This is very important concept called pure culture. We will explain real quick. So what happened is, if a person has TB, tuberculosis, then the sputum sample should be isolated to get tuberculosis, microbacterial tuberculosis. Okay? And we get the pure culture. Not only a mixed culture with other microorganisms, it's a pure culture. Number 3 is the pure culture infected, or we say inoculated into a healthy organism will get same disease. Now we cannot do this in the human being. Is that right? So what we do, using experimental animals, by the time what they can do is a kind of a guinea pig. Just a simple guinea pig, okay? If the guinea pig injected with TB or inoculated, that could be died. Usually those experimental animals are pretty much immune ability is not very strong. Because if they have a very strong immune ability, will become another story, it will make it more complicated. So those experimental animals usually easily to get sick and easily to be died, because we want to see the outcomes of those pathogens. So it's died. Last thing, the same pure culture can be re-isolated. That means in this sick and dead guinea pig, in the lung area or sputum sample, we could be isolated, get the same tuberculosis. That is the whole story, the theory of the Koch postulation. It is well explained the relationship between microorganism and a specific disease. Here, which is explains a tuberculosis causing a guinea pig has TB. But we want to point it out that when Bob Koch mentioned about this concept, this theory, it is about 200 years ago, at least 100 to 150 to 200 years ago. And by the time, there is no concept of immunology yet, and there is no concept to come out with asymptom. So right now we know, if you use this theory, the number one item may not work very well. How many cases in the world is asymptomatic of coronavirus? Lots of people using antigen test or even nucleic acid test tested positive but didn't have any symptoms. Although I don't believe it, but they true has those cases reported by CDC. That means the healthy people could be carry on this microorganism but without showing any symptoms, showing any of the disease. Do you remember a very famous basketball legendary is Magic Johnson from the LA? He had HIV virus rest of the most time of the life, and still good. And the people scared to play with him in the NBA games because in case he's broken his blood, then it could cause transmission. Is that right? Could cause infection. So these are some of the examples. Just want to tell you one thing is that's not really necessarily true if you fit today's story, because when they developed this theory, the immunology and the asymptomatic concept has not been established yet. But it is really a good start to talk about the relationship between microorganism and a specific disease caused by that microorganism. Next, we want to talk about the pure culture. This is a big thing here, and it is difficult to get. We want to talk about this pure culture. So, first of all, in the history, there is a big debate about how you're going to get a pure culture. And I tell you one thing, we just mentioned about Louis Pasteur and Bob Koch. Look at the timeline, there's about 50 years they overlapped. Do you think they're friends? No, they are competitors. By the time both of their lab, both of their group want to get a pure culture. So there is a two-way to do. So Louis Pasteur group think about, I'm going to be doing this in a liquid media. How we do this in the liquid media is doing serial dilution. This is one of the skills we will be training you in the lab, but you already did in your biochemistry or organic chemistry class. You have multiple tubes. Okay, let's say I have a broth right here. This is a bacterial broth. I have 10 to the 8 cells. I'm going to do 10 or 100-fold serial dilution. We're using multiple tubes to do the dilution. And at the end of the day, we hope theoretically, somehow, in the last tube, there will be only one cell. That cell means pure culture. Is this going to work? Theoretically, yes. Practically, no. Because you're never going to figure out the liquid tube has exactly one cell. Or they have two cells, but those two cells are the same genus name and species name. It's very difficult to do. So that way didn't work very well, to be honest. Now, Bob Koch's group think about you have to use solid media, not liquid media. But the material for this solid media is challenging. It's very difficult to find. Why? First of all, this medium has to be melted at a high temperature. You have to be melted around, let's say, 50 degrees Celsius. Secondly, it has to be solidified around 25 to 30 degrees Celsius. Because it's easy to preparation. Number three, bacteria can use it, but not block it. It is hard. And at the beginning, they tried a lot. And in the history, there is a very important person who's doing this research. His name is What has he? What has he trying to do? What has Hesse trying to do? Find the material using for solid media. He tried jelly at the beginning. It didn't work very well. It's like you grape jelly for the sandwich you did in the morning for the breakfast. The bacteria can grow there, there's no problem. But if you grow in bacteria, the color will be changed and it will be broken. So certainly it's not good. So what has he spending many days to think about it, even months. There's a very one hot summer in German suburb of Berlin somewhere. His wife, Fanny Hesse, is one day making French pudding. And it's a very hot day. Okay, no air conditioning by the time. It's about somewhere 95 to 100 degrees Fahrenheit. So 35 degrees Celsius is very hot. So what has he still working? The Fanny says, honey, the French pudding is ready. We can have a lunch. So they go to the backyard and to have the lunch, and what has he think about is the French pudding. The material made for pudding, what is that? It's an agar, is that right? It's polysaccharides from the seaweed. Well, I want to mention, right now you have a different kind of French pudding. If you go to Montreal, Canada, you get all kinds of those stuff. It's completely changed compared to 200 years ago. By the time, it is basically polysaccharides. So polysaccharides of seaweed. That is what we call it. It's agar. So, Fanny Hesse told Walter Hesse, and then Walter Hesse did a bunch of the experiments, told Bob Cook, and they find that the good thing is agar. This is where it comes. An important solid media for isolation pure culture. It is agar, is a polysaccharide extract of seaweed. This is a Fanny Hesse, the first woman, a very smart housewife, and finally become a big person in the microbiology area, and later on she joined Bob Cook's group and did other things. But that contribution is really